Okay, so that's the first one. Okay. Then the other one, we can say, okay, so let me make a comment that, um, so this is to compare performance of R squared or sample variance, sample estimators, performance of estimators of variance, right? Variance of a data set. So that's the first one. The second one, we'll use the same principle, which is 6 squared. That is going to also take, and why am I using only X? Because this one, it takes just one sample, right? One vector or whatever you want to call it. So this, if I want to use this one, then I need, how do I get N? How can I get N? It was, yes, how do we get a size? If I give you a vector, let's say I collect our age, length, good. So you don't have to forget some of this. Length. So length will give you the sample size of a vector, length X. Okay, so that's all I need. So the first one is just a variance. So this is MLE estimator of variance. And this one is what? The sample variance. Not the sample variance. It doesn't really have a name. Let's say normal variance. Normal sample variance. Like that. Okay. All right. So what do we do now? We haven't finished. So we can say that our estimate is equal to what? N minus 1. Okay. Then we multiply that by what? Var X. Do you agree? Then I divide by what? N. Okay. Then because I want this, I return EST estimate. That's it. That's our simple function for computing this. Is everybody okay? Is everybody okay? You can also sum, okay, minus the mean square. And I mean, it's up to you. Yeah. Yeah. Sure. Okay. Okay. So now we have our estimators, isn't it? Written. What we need to do now is to now simulate observations. So we may start first with any distribution. Okay. So 1, A. What distribution do you want us to start with? Maybe exponential distribution or normal or what have you. Okay, so let's use normal distribution. Okay, so I'm going to start with 1, but you can, when you finish, you can do it as a data frame and so forth. Normal distribution. How do you simulate? So let's say our data, and you see small d data is a keyword, right? So you don't use data like that. So that will be our norm. So here I'll need certain things. For example, the sample size. Usually that's how you do simulation. There's a sample size you will choose. So maybe I start first with 10, then I'm doing this. After that, I'll automate it and so forth. So for you to see. So our norm, remember, if you don't remember, just do our norm. And then you come here. Why am I using our norm? Who can explain to us? We want random observation from a normal distribution. So here we are interested in the standard deviation, the variance, right? So n is 2. We also need the parameter. What is our parameter? It's the variance, right? Yes, but normal distribution needs what? It needs what? No, it's rather standard deviation. So the variance is standard deviation squared. Is that okay? Yeah. But remember, the standard deviation cannot be negative. So we can say that our well, if we like, we can rather be, if we can also check it at the standard deviation level. Do you get it? Other than that, if we want the variance level, then we need, let's say, var. No, it should have been sigma, right? So sigma, you see, I've used capital S to distinguish it from the inbuilt function sigma. So if it is 4, then it means the standard deviation is what? 2. Good. So it means that whatever I have here, I have to do SQRT. SQRT is what? Square root of what? Sigma. Is everybody okay? Is everybody okay? If I do this, I don't need to be changing the codes. If I type in the data, then it means every time I'm changing the sample size, I need to go to the code and we don't do that. If you later on, if you are doing simulation for your masters, you realize that every day you have to go. So that's how you define everything at the top and then you run your code. So the mean, I can choose anything, right? I can let it be because my focus is on the mean. But I must tell you that when you are doing simulation, sometimes your mean will, another parameter will have influence or some influence on the other. So in a simulation, you need to vary that one as well to see its effect on your estimate. Okay, so now let's see. If I come here, I can say the data n is equal to n, mean is equal to, and then SZ is equal to that. So I can, oh, n is not because I did not run this. Then I need to run this. I need to take this up there. Oh no, okay, no. It should be here. Okay, sample size and variance. So what are we doing? We know the variance is 4, right? But we are now going to use our estimator to estimate this variance of 4. Is everybody okay with this? So the estimator that will give us the value of variance closer to what? 4 is the best. Because we know it. But in real life, that's not the case. Okay, so let's see. So we can now simulate. So I can look at my data. This is what I get. If I don't want it to be negatives, I can choose a mean of like 100 so that I shift it the positive side. Okay, maybe we should do that. You see, this one doesn't have any. Okay, your own will be different from mine, right? Because we are not setting seed. If we want to get the same results, we'll set seed and move on. Okay. So now let's call our functions. So SQR, if you have to run it for it to take effect. And if you come here, oh, I should clear all mine. So let me do it this way. Okay. And then I go there, I do data. So my data is there like that. So now I can call those functions to compute the variance. So let's see. I can call SQ. What was the first one? Oh, S dot square. I don't know why it is not showing now. Yeah, there it is. S dot square. Then what do? I'll put the data in, right? You see, my variance is what? Is 1. What about this? We can check. If you are not following, please draw my attention. 0.9. Is everybody okay? The what? What do you mean by X1? Yes. It's giving you error. Just the variance. Which one? The first one. This one. Why is it giving you error? It's just this. Variance of X. That's all. Can you explain why? Okay, let me ask you. What if I had done just variance X? What do you think will happen? Yes. Can I take this one off and do something like this? Why? Why can't do so? There. But it will now be calling what X is. So if you do this, it means you have to define your data. I mean, we could do it by saying data. If I use data, that will be fine. Is that okay? Yeah, that it will do it. So that's why I did a function so that it becomes what? Easier to do it. Okay. Okay. So is everybody okay? Now I can increase my sample size. You see, when it is 10, we go to what? 1, which is far off. So let's see. Have you seen what I'm getting? 4. 4.05. So okay, so just these two, what principle does it tell us in statistics? We got n is equal to 10. The variance was somewhere 1. Now n is equal to 100. Look at what we are getting. Almost close to the parameter. What principle is that? Just centrally between. It's law of large numbers. Which one of them? Which one? Weak, strong? What is the strong one? And what is weak? Because it's weak. As what? It's not just a mean. Law of large numbers is not just about the mean. You are giving an example. So the sample, your estimator, the estimate from your sample will get closer toward the parameter as n increases. And that's what we are witnessing here. When n is, we say that if theta cap n is your estimate, then this will tend toward theta as n approaches 1. Yes. So you see, then that's what we are demonstrating with n is equal to 10, n is equal to 100, and so forth. I can change n. So you see now, I'm not touching my function. All I'm touching is just what? The end, what I need to run it. So if I change it to 1,000, it's not even working well. But that's simulation. That's why you don't do it just once. You see, I did 100 and I was close to 4. Now that I did 1,000, I'm even far away from that. And this is a normal distribution where you don't expect to get outliers. Do you get what I'm saying? You don't expect to get outliers, but you see it is even fluctuating. So what if I now get those right tail distribution, F, T, and Pareto, and log normal, and so forth, where you can get an unusually large value? What do you expect now? So those are some of the things. So this variance, we can also add, yes, we can also add, let's say, the mean or the median absolute deviation or the median squared deviation, where we'll, instead of the mean, we'll find the median and so forth. So that one, you realize when we simulate from a log normal or a Pareto, that will do better because the mean, these ones are, they are based on the mean. So if the mean is distorted, you expect your variances to be also be distorted. And so, okay. So we can do it again. I can rerun it again. Then the mean, okay. So I can rerun it again. You see, now I'm getting something close to it. So this is why simulations, and that's why I'll check you see. So each time I run it, because I'm generating new data, I'm going to get different results. I get different results. I get different results. I get different. Some will be close to it, others not, and so forth. You see, the same 1,000. You see what is happening. So that's why here you will get different values because each time you are simulating, even though it's from the same district, the values will not be the same. If you don't understand what is going on, I simulate on the basis of the normal distribution, the same sample size, the same parameter. But each time I run, it generates different set of random numbers from a particular distribution. That's why I'm getting the variance. That's why you do it several times and then you can now average it. Find your mean square error. Pardon me. Which one is not working? This is not the function of me. I didn't know this one. Check. But you have to comment this, compare it, comment it. That's what this is telling you that it will plan. And you can increase your font size. Okay, so the square. Yeah, so now run it says. Yes. object X not now. I think it is important. Oh, no, you put your functions together. Do not look at my problem. So, look over here. Each of them has, so you need a keyword function. Remember, you open a curly bracket. Why did I do this one this way, that one, no curly bracket? Actually, the curly bracket should come. But if it's on the same line, you don't need it. The file is just one line of code, so I don't need to provide one. But this one, I have to find the length and then it's so forth. One side. Go to, edit, and then it's Is everybody okay? Can we move on? So this, the principle is two, and then now you couple with what the okay. So now we can move on. So I think now the way we are, everybody is okay. What we need to do now is to now get these values instead of running them, and we'll keep them in what? In as a vector, right? Or as what? In a data frame. In a data frame, we can have either two columns, right? Each one for this, one for that. All right. So what do I do? There are several ways you can do it. One way is that I can then generate all the observations and keep them in a data frame or a matrix. Do you get what I'm saying? So what I'm going to do, so I said you should watch some video on what the apply functions. So that's what we're going to do. So we can generate our data this way. Either these will be samples. So sample 1, sample 2, sample 3 up to sample I. That's the repetition. Then over here we have what? The sample size, maybe 10 or 100. So it means that if I take sample 1, I have 100 observations. You get it? So I get a matrix of 100 by, let's say, 1,000. Becomes so huge. Yes, by 1,000. Now, when I take my functions, I'm going to apply the function to each row because each row is a sample. Just like we did data. So it calculates this, I get 2, it calculates this, I get 2, and so forth. So that's the concept. Please look over here so that when we get to the programming aspect, you are not confused. I have 2 estimators. I want to generate several observations. As I said, one way is to generate the data, then you find the variance. Another way will be that each time you generate the data, you calculate the variance, to generate it. I usually will go by this. When I'm going to do this, I can even store the data so that if I want to come back. Okay. So what we are going to do is that we can use the apply function to generate a data of this form. One sample size, but different samples. And your R is the number of repetitions. Is everybody okay? Once we get this, then when you take this, it's like the data that we did. We found the variance and so forth. So that's what we're doing. One. Yeah, so if we take sample 1, we will calculate R squared and sigma cap squared. Like that. Yes. So I can write another function that takes, so that's how you let your functions communicate. Yes. Yes. So put this one in quotation marks so that we can call it within another function and rerun it. So you put the name in quotation marks. It makes it available to all distributions. So what I'm going to do is that I'm going to define another function which is called var.fun. And var.fun takes so this one, I'm going back, I'm creating a function to compute, or let's say a function to compute both variances. So I'm just calling the previous function so that I get the variances computed at once. That's it. So when you are programming, you do this, you do it in bits so that when there's a problem, you can easily trace it. So you do the functions in bits and pieces, and then you now be calling them. So if I show you some of the programs we run, you will see that I may have 1,000 like lines, but they are just functions calling one another. So break your things into different functions. It makes life easier. So this one, I can just say that this is C, right? C is what? Combined function. Yes. So I just need a vector. So S dot what? SQ. Then I find X, then comma. I do what? Sec dot square X. That's all. So let me call this, and then you see I'm going to call var.fun. And then let me put in data with simulated data. So you see now it will give us that instead of separate previously we were getting them separately. Now I'll put them together so we have this one and that one. Then we name it. We can name it as well. Okay. So if I want to name it, then I need to go back and put them in what? In a vector or something like that. But I'll hold on with the naming now. Is everybody okay with this? So we are going one step at a time. Yes. Yes. So now you see, I am now calling the functions that I created up. I'm also now going to create a function that also called the var function. When the var function is called, it is also going to call what? scale. So it's like it's like that. Like this. Okay. Okay. And when you are doing this, you go about one step at a time. Then you check it works. Then you can put them together. All what we are doing, if I finish, I can just write one function to call all of them, and everything will then be done. So that's how we do this. Yes. Okay. So now what I'm going to do is that I'm now going to simulate observations. So the data, how am I going to simulate it? I'm going to use, so I'm going to set a counter from 1 to R. So it means each time I'm running this simulation, I need R. So I'll go up there and give R, right? So R is maybe 100. That is number of repetitions. Good, okay. So I need a function. Yeah, I should have done it in such a way that I'm not going back and forth, but it's okay. Um, so R, now I need my data. So let's see how I'm going to do that. So generate data matrix. Okay. So how am I going to do the data? Okay, so data, I call it data math. So I use the sapply function. Okay. Sapply means take whatever list is been given. So 1 to R, you remember is to 1 to R, meaning 1, 2, 3. So if I say R is 100, it is going to take the first one, put it in second one, third one, and so forth to 100. What function am I talking about? The function is, let's say, X, and then I'm going to put this, so I don't need the data, all I need is random sample. This one. So what I have done is nothing more than just take 1 to R is 100. So when X is equal to 1, okay, it will take 1 and it will say X is equal to 1, go in. Actually, it doesn't really take any X, right? The X is not being used in the function, but it will just generate this R times. Okay. To make it easier, I'm going to let the n be small. Let's say n is 20, and then the repetitions is 10, so that you will see what is happening. So, yes, let's see. So now I'm coming here. I'll run this here. Okay, so data math is what? It's a matrix made up of what? 20 rows and 10 columns. Which one is a, so what is your sample now? Is it rows that are your samples or columns that are your samples? No, look at it, don't guess. Yes. How will you know which one is your sample, which one is your repetition? How many repetitions are we getting? 10. Where is the 10? It is what? No, the number of columns. So it means each column is a sample. Is everybody okay with this? Is everybody okay with this? Yeah. I can also make rows the sample by putting T in front of the, putting them in T, which is transpose. Is that okay? So I can put everything here in the function small t. That's why I said you should not be using T to name your So if I do this, you see now it has changed. So the rows now becomes what? My sample, and then the columns become my what? My the repetitions. Yeah, you are getting error. Hey, we have not reached anywhere. This is it. So C. So the principle is that I want to get a vector of two values. So it has to be a vector. Is it done? Sigma is cap. But is it even sigma? It's not sigma. It's SQ or you did a sigma. Yeah, so check the name of the function. Yeah, it's wrong. Okay, can we move on? Can we move on? Or you are still. So generate the data matrix, we are done. So now we are saying that each row is our what? Our data. So I'm going to now apply the combine function on each row. And if I do that, each row, it will compute the var, the S squared, and what? The sigma. So that's what we're going to do. So here we're going to say compute the variances. So to compute the variances, I'm going to use apply function. The apply function, so that's why I said that function is very important. It makes life easier. Whatever we are doing, so you can also use the for loop and repeat and so forth to do it. But I prefer to work with the apply function. So what is happening is that we're going to say apply, and then the apply function, we apply, so we take our data, let's say data, then you have a margin. This margin, if it is equal to 1, it means take each row as a row. If it is 2, it means take what? Each column. But here, our samples are in rows, so our margin will be 1. Then what is here is on the function you want to do, which is var dot what equals var. So that's what we're going to do. Okay. So we will say S squared dot, or let's say var variance, so var dot esc. It has so many, so you have to be careful not to make your name. So I'll do apply. If check the apply functions to see how we use them. Oh. So when you come here, say apply functions over array margin. So apply, this is how it is done, but so you see here, it is telling you that what? Sort the columns of a matrix. Why is this so? Because the margin is what? 2. If it is 1, it will sort what? The rows. Okay, so please take note of that. Okay, so apply. All right. Then my X will be what? Is data math. So which is, then I'll put 1. And then what do I need to generate? What do I want to calculate for each row? You come to var.fun, right? Yeah, var.fun. So you can just put var.fun there and do this. Wait. Fun is missing. Okay, I know what is happening. So you can do function x and then you put x here. Argument fun is missing. Let me see data math. Yeah. So what's the problem? What is the problem? Fun. Yeah. Okay. So I don't need any x in there. Okay. So something like this. So now, if I go to over here, I'll see var.estimate. You see it's all numeric. One, it has 2 columns, 10 rows. No, 2 rows, 10 columns. So row 1 is for the what? S squared. And row 2 is for the maximum likelihood estimator. That's how it is. If I want it to be this, I'll use T to use it. So I can display it for you to see. Okay, so these are my estimates. Do you remember the variance? The variance is what? 4, right? So what we did, it means our estimate, the first one, the estimate is 2.71. Maximum likelihood is 2.51, 3.2, and so forth, 5, and so forth, and so forth. Is everybody okay? You guys. No, you have to be careful with the naming. So this one is small letter. Sigma is a function in R. That's why when I'm using that, I use cap. Then it differentiates it from all the things. So if you put small letter, it won't give you anything because you are trying to calculate square root of a function. It won't work. So please. So why did you name it sigma? I said sigma, so it's just one. I don't know why you are repeating it in there. Okay. Is everybody okay? The way we are moving, one step at a time. So now we have variance estimate. The next level is that we want to find maximum likelihood. Sorry, which one? Yes, take the x out. If here, apply. So just the data. Don't put, if you put x, then it requires you to now say, so if I put this one, I can even take this function of, but I won't take it. That is the usual way of doing it. I can also take it off. It's the same as this. Let me put this one. So you can do it like this, like that. Okay. You get the same thing. Yeah. So it calls that function, and for each row, it computes that value. So it's the same. If you put a function in front of it, it's the same. 2.71 to so and so. All right. Now we've gotten estimates. Okay. Shall we move on? So where we reach is that we now have estimates like the table we have over there. Is that okay? Now we want to compute what? MSE and bias. So you remember bias of theta hat of theta, we said is what? The mean, the expected value of what? Theta minus theta, right? Okay. Now, in this case, how do you do it? So we will calculate a function which will call for the mean, and then we subtract the value. Is everybody okay? So now we will go back and write a function for bias and a function for mean square error. Is everybody okay? Is everybody okay? Good. So how do we, let's say, function to compute bias? Should we do them together? Bias and MSE. So we will call the function bias MSE, which will be a function that takes in x and the parameter, or it takes x and what? Theta. Is everybody okay? It has to take some data, or we can say theta hat, yeah, theta hat and what? Theta. Because if you don't have theta, you can't, yes, you need the theta hat, theta. Okay. So then we open, then we say bias will then be equal to mean of what? Mean of what? Theta hat. Is that okay? Minus what? Theta. Sometime maybe when you are plotting, you can also find absolute bias because we want the one that is closer to 0. If you do it this way, some will be negative, some will be what? Positive. Then MSE will be what? The mean. Is that okay? I can find the mean of what? So I'm finding 1 over r all squared. So what I'm going to do is mean of theta hat minus theta all squared, right? Is everybody okay? Is everybody okay? But this one should be okay. No, not where? Which one? Which one I found? This one. This one. So there's a mistake here. Put your best at the last time. There's one. You have to work within the bracket. So you need one more bracket. So once you have that times, it signifies adopted a job. You must address it before you move. I must say that when I was doing that, nobody had that time to do this. Professor LaRouche will now come and check whether you're a black person. So there are so many mistakes. Bracket, so this bracket does not have. So you need one bracket. Good. So always you have to work with the organization. That's how the development. The value is up there on the same 10. Because I wanted you to see, I made my repetitions 10. But the previous one was 1,000. So if you do it, you can, when you display it, it will just, be all over the screen. Okay, let's hurry up and do this. So now I have function to compute bias, function to compute what? Mean square. Then I can put them together and say it is called tab, and that tab will be what? C, bias, and what? MSC. Then I can name it names. Why am I using names? Because this is a vector, right? tab. And what would I have to do? I will say one is what? Bias, and the other is what? MSE. And I'm done. What do I do for this function? I need to return the values. If I like, and we can round it, right, into some maybe 3 decimal places or 2 decimal places. So if we like, when we are tabbing it, we can round it. Round to what? Maybe 3 decimal places like that. Okay. And then what do we return? Tab. So this function, I can now run it. It doesn't take anything away. Sorry, like there's no error. So now my variance estimate, I can now go and what? Compute the bias and what? The mean square error for each of those values. Remember that my variance estimate is also what? One of two, so it's for rows. So I now use the same apply function. The same principles that you are using. So I can say apply. Okay. Then I take my var.estimate now becomes my data. Then for each row, what do? I find what? The bias MSE. That will give me what? 2 values for each of them. The first one being bias, the second one being what? Variance, the MSE. What happened? Oh yeah, we don't have theta because we need to say that theta is equal to the sigma. Is everybody okay? Yeah. So now the challenge is, how do you do it? Well, that's why I put the function there. You remember the first one, I put function there. So here I need a function. I need X. But when it comes to bias math, I need, what was the theta hat, right? Theta hat is equal to what? X. That's the value you are passing through. But the theta should be what? Should be, sometimes it works, sometimes it doesn't. So theta will be equal to what? Sigma. Okay, let's see. Sometimes, if you're lucky, it works. Yeah, it works. Okay, so there it is. Okay, so you are still having, I'll send you the script anyway, but you need to understand the concept. So I'm going to make a comment that compute bias and what mean square error using the function. So we use our function, but this I need to BM so bias MSE dot est is that okay. And then when I finish, I can name this. The columns are not named, right? So the first one is what? Is the R squared. The second one is what? The MLE. So I can name it. In this case, I'll say call names. We can even do it in the function directory, but it means that you need to compute it and then name it before you return. We compute the values and then we name it and then we return it. We can do so, but it means I have to collapse this, right? And do it. I won't advise that because we may also change Yes, the code. So this one, the bias code. Next time, because I don't write any function for bias because I've been doing this over and over and over. So I just write one function. I make it general. So like what I have done, bias and so if I'm doing 3 estimators, now I have only 3, then I name it. Do you get what I'm saying? If we name it inside, it means if we change now to another, yes, we have to go and change. So yeah, cultivate that. Otherwise, you in that case you don't work extra to do this. So we can name it outside. Don't worry. So we call names. So if we change the sample size, you will see it over here. So when you go home, you do so. When we are done with all this, we are going one step at the other. If I'm programmed, that's what I do. So at the start, I do this. Once I finish and everything works, I now put everything in a one function. So then the computers over there, I can now send it to it to compute everything. When you go, you are only collecting your bias and MSC. So that's how this is that. So now we do our core names. Okay, and the core names will be what? How do we name it? S squared, right? So that variance is what? S squared. And then you have which one? MLE. We can say MLE estimate. Okay. So now if you display this, you have S squared and MLE. So the question is, which one is better? Which one is better? In this case, MLE, right? Because it gives you all lesser bias and also lesser MSC. No, we are not using P2. That is proportion. Yeah, the proportion. So that's the logical thing that we want to do. We started saying that there's this S sigma squared. We want to assess their performance. We generated from the normal. So now when you can generate from exponential distribution, you can generate from a normal distribution. You can explore, change the sample size to see which one is more consistent. And so that's the sort of happen with, let's say, in database. That's you see, that's why I said functions in that are very important. But that's what you are going to do all the time. Some of these functions apply. The next thing we will do will be the bootstrap. So when I come next week, we will going to take bootstrap. It's the same principle. But now these ones are well developed. They will have a function to do, but you have to know how to use a function. That's an inbuilt function. Yes, there's an inbuilt. Bootstrap is an inbuilt. Boot is an inbuilt function based on what? But there's a bootstrap. So you need, if you want to use bootstrap, you need to install it. There's a package called the so let's see, boot. So you see boot. So boot is a function. What do we call it? A system function, not user defined. So you see boot. Yeah. So bootstrap functions originated by Angelo Canti for S. Yeah, but there's also bootstrap. Bootstrap. So you can install this bootstrap as well. So we will do bootstrap. So I think in statistics, there's a course on this. I was even discussing with HOD that we need Maybe they say at the PhD level, like think at the master's level, if we even introduce it an elective. But you need it if you want to survive. It will be difficult if you don't know how you're going to. They are said unless you are able to prove analytically. And even that, you need to demonstrate. 3. If it is, yes, or more. Here you see, we did not. I could have also added normal distribution mean. Okay, the mean I can choose, let's say, the simple arithmetic mean, the geometric mean, and then the harmonic mean. So I can compare them, how they estimate the actual mean. So then it means we are going to get five parameters. The other one, when we are computing bias, we are going to use the mean, which is 100. Remember the actual mean we put in the is 100. Yeah, but the sigma was 4. You can do so. Okay. So let me stop this and then send it to you.